Hey everyone, we're going to do a walkthrough of minimum cost to convert string number 1, which is one of the most fun contest problems we've had in a while, so let's get into it. So we're given a source and target string, original and changed array, as well as a cost array. We're also told that we're only allowed to do certain transformations. One is where we pick a character x from the source and change it to y, only if there exists j such that original of j is equal to x and changed of j is equal to y. And the cost of such an operation is going to be cost of j. And now we're told to return the minimum cost of changing source to target subject to those constraints. Okay, so here's an example. Let's say we're transforming the source ABCD into target ACBE. And let's say that we also have arrays original ABCCED mapped to changed array BCBEBE. And let's say that the cost array is 2551220. Now, initially we might think that we'll have a dictionary that maps original of I to changed of I, along with the minimum cost of changing original I to changed I. So for example, we might have A mapped to B2 because the cost of transitioning from A to B is 2. Then we might also have C mapped to B of 5 and E of 1 because C can transition to B with cost 5 and to E with cost 1. And then we might try iterating through our source word and just choosing the minimum original I to changed I that we can find for each index. But the reason this doesn't quite work is apparent if we read the first example case closely. First, let's explicitly show one more entry in our map so we can better understand this. The transition from E to B has cost 2, so we show that entry in our map. Now, let's see what's the minimum cost of going from C to B. If we go from C to B directly, we get a cost of 5. However, we can also go from C to E with cost 1, followed by E to B with cost 2, which gives us a total of 3. So in fact, we may actually need to transition through many letters before reaching our target if the cost of transitioning directly is too high. This should remind you of a very famous algorithm. What is it? If you don't know, think about it and pause the video. I'll reveal the answer in 3, 2, 1. The answer is this should remind you of Dijkstra's. You can imagine that all our letters are nodes in a graph, and there are directed edges between them with weights described by the cost array. In this example, we would draw a directed edge from A to B with weight 2, then B to C with weight 5, C back to B with weight 5, and so on. And then when we iterate through our source word, every time we find a letter source of I that differs from target of I, we run Dijkstra's algorithm on the graph, searching for the minimum path from source I to target I. Okay, so assuming you've got this down pat, this problem really just boils down to implementation. So we're going to spend a little bit more time on coding than we normally do. Alrighty, so first off, we need to construct our graph. We're just going to use the dictionary representation we talked about earlier, where the source letter maps to another dictionary, in which the target letter maps to the cost of transitioning from source to target. So we'll iterate through our original word. If the original letter does not yet exist in our graph, we add an empty dictionary. Otherwise, we set the result of transitioning our original letter to the minimum of cost I and the existing cost of original letter to the target letter. We do this because they told us in the problem description there could be repeat entries in both original and changed arrays. So at index 0, we might have A to B with cost 2, but then at index 3, we might have A and B again with cost 1, in which case we only want to keep the edge mapping A to B with cost 1. So if original letter to target letter already exists in our graph, we take the minimum of that value with cost I. Otherwise, if it doesn't yet exist, we take the minimum of cost I and infinity, which is of course cost of I. Alrighty, so that's our graph construction. Now let's get into the meat of the problem. We set our total to 0 and we iterate through our source word. If the current letter differs from the letter at the same index in the target, we do a search through the graph from source I to target I. If the return result is -1, we immediately return -1, because that means we weren't able to find a path from source I to target I. Otherwise, we add the returned result to our running total, and then we return total. And now let's define this find path routine that we called from the main function. So we'll use the Python priority queue for this guy, which is basically a min heap. We're doing this just because I like the priority queue API better, and it basically has the same functionality. So we'll initialize it with a tuple with cost 0 and the source letter. Notice here that I'm specifically putting cost 0 before the letter. The reason is that the priority queue will do a lexicographic sorting, which means that it sorts tuples based on the first element followed by the second element. In Dijkstra's, we want to greedily explore the nodes with the smallest distance accumulated so far, so we want to sort by distance traveled. Therefore, we put the cost first before the letter. Then we'll say, while this priority queue is not empty, let's pop out the current cost and letter. If the popped letter is equal to the target, that means we've reached our destination, and we can return the accumulated cost. Otherwise, we need to add each neighbor of the popped letter to our priority queue, along with the cost of traveling to that neighbor. So we first do graph.getLetter, because that will get us all the neighbors of the current letter. Then we iterate through that map, and we put cost plus neighbor's neighbor, along with the neighbor itself into our priority queue. Neighbor's neighbor will just get us the cost of traveling from letter to neighbor. Outside of this iteration, we return -1, because if we never hit this condition where the popped letter is equal to the target, that means we didn't successfully find a path from source to target. Now, a couple finer points. First of all, we need to deal with the possibility that we may encounter cycles in our graph. To address this, let's additionally add a set called seen. We only explore the neighbors of the popped letter if the popped letter has never before been seen. And once we do see this letter for the first time, we immediately add it to our set. Now, let's say that the letter H is in our priority queue multiple times. Why is it okay for us to only explore the H that gets popped out first? Well, since the priority queue is sorting by cost, the first H that gets popped out will be the tuple that represents the smallest cost to get from source to H. So it's okay for us to ignore future occurrences of that letter, because future occurrences of the letter H will have a higher cost. So that's the first finer point. Now, if you submit this code, it's technically correct, but I believe you'll get time limit exceeded. To help you out, let's introduce this memoization map, which basically maps the tuple source target to the minimum cost of going from source to target. So in our find path function, the first thing we need to check is if source target has already been evaluated. If so, we return the memoized result. And inside of our actual pathfinding algorithm, we'll save the result of our pathfinding to the memo map before returning the result to ensure that we don't repeat work in the future. And now if we submit our code, we do indeed get an accepted solution. Now, there's probably further optimizations you can do to get this to go even faster, but hey, this was a contest problem, so we really just want to get this working with the cleanest code possible. If you found this helpful, please like, comment, and subscribe. I'll see you in the next video.